Hey guys, this is a 3.7 notes. It's called Transformations of Polynomial Functions, but it also deals a lot with something called symmetry, um, which we'll start by going through symmetry now. So symmetry is when an image or point is identical after a transformation. So image or a point is identical after a transformation. Okay, so symmetry about the y-axis, right? So whenever you do a reflection of the y-axis, right, it's the opposite of x. Okay, so if xy is on the graph, then negative xy is also on the graph if it's symmetric. Okay, for the origin, right, it's the opposite of x and y. Right, so if it's symmetric about the origin, then our xy and negative xy, negative x, negative y, is also on the graph. Okay, and then lastly is about the x-axis. So this would be opposite of y, right? Because right here's your x-axis, right? So if it points up here, its symmetric point would be right here, right? So it's your opposite of y, right? For the y-axis, right? Right, if your point's here, the symmetric point is the same distance on the other side, right? And your x is the opposite of what the other x is, right? And then about the origin, oh, I'll make it a different color. Okay, so here's our origin, right? If we have 1, 1, right? The negative 1, negative 1. Okay, those are symmetric. Okay, all right. So that's essentially the naming of symmetry. Now we're going to go into the different types of functions you get. Okay, so we either are going to have an even or an odd function. Okay, there's two ways to prove these. One is graphically and one is algebraically. Okay, so graphically, our function is going to be even if when the graph is symmetric about the y-axis. Okay, so here's our y-axis. Each point, right, is symmetric to right, and it's our opposite of our x's, right? So you think of like x squared, right? We know that's even power, right? It's an even function, right? And we can tell just looking at the graph because the points are symmetric about the y-axis. Okay. And we can say an even function has y-axis symmetry, right? So, right, draw y, draw a line through y. Right, every point on the graph should be symmetric to the y-axis if it's an even function. Right, all these points you can see are the same distance, just on the opposite side of that y-axis. Now, to prove algebraically, say we're just given a function, right, not a picture, right, we can tell that it's even when negative x is substituted in for x and the equations are the same, right? So algebraically, for even, equations are the same. Right, so you substitute in negative x for x and it still remains the same, right? Because when it's raised to an even power, whether it's negative or positive, it's going to be turned back to positive, right? Because when you square or to the fourth power, any number becomes positive. Now, let's look at odd functions. Graphically, right, when the graph is symmetric about the origin, okay, meaning, right, our points are opposite to each other. So when negative x is substituted in for x and negative y is substituted in for y, the equations are the same, right? So meaning the equation ends up being opposite. So that's algebraically, right? But if you think about it, right, here's our origin, right? Here's 1xy, so it's at 3, 4. That means if it's symmetric about the origin, it needs to be -3, -4, which it is. Okay, so an odd function has origin symmetry. Now, the last one that we did talk about before was x-axis symmetry. Well, if a graph has x-axis symmetry, it is not a function because it does not pass the vertical line test. So, I'm gonna move this up. So, if x-axis symmetry, it is not a function because it does not pass the vertical line test. Okay, so right, for example, right, if right here's your xy, right, and your function looks like this. Well, the picture looks like that, right? Your vertical line test, if any of the same points hit vertically, it is not a function. And any picture that has x-axis symmetry is never going to pass that vertical line test, right? Because it's going to have the same point above the x-axis as below the x-axis, so there will be 2 points for each x value, right? So it won't be a function. All right, so now looking at these certain graphs, we're going to they have they're even or odd functions, right? Or they are not a function. Okay, so remember, even means y-axis symmetry. Odd means origin, right? So xy and -x, -y, and y-axis is xy and -xy. Okay. If remember x-axis symmetry, not a function. Okay, so let's go through these. If we look at 7, right, you can tell we have the same point here as here, right? And this is, if this is xy, then this would be -x, -y. So we have origin symmetry, which tells us it's an odd function. The next one, right? We have the same points, same y points in opposite x values, which tells us it is y-axis symmetry. So y-axis tells us it's an even function. Now, this next one, right, it doesn't even cross the y-axis, and it doesn't cross through the origin, so this one would be neither. Right, it is a function, but it's neither odd or even. Okay. Number 10, right? This should be y-axis symmetry. Right, same y points for opposite x values. Right, therefore it is even function. Now the next one, right? It's not the same opposite x values for the y, so it's not y-axis, and right, it's not. If you picked a point here and here, right, they're not opposite x's and opposite y's, right? They're not. There's nothing below our y-axis, so they're neither even or odd. Right? It's not origin and it's not y-axis. And then number 12, right? This is also neither. Right? There's no opposite x's or opposite y's. So if you want to try these on your own, you can pause it now and then I'll show you the solution. If we look, A is origin, right? They're opposite. The x's are opposite and the y's are opposite for the symmetric points. And then the next one, right? The x's are opposite and the y's are the same. Therefore, it's y-axis symmetry and even. All right, so now we'll do it algebraically. Okay, so again, right, even, we know is y-axis symmetry. So what we to prove it's even, when negative x is substituted in for x, the equations stay the same. Right, so negative x for x, equations are the same. Odd, right? Negative x for x, equations are opposite. And then neither, right? Right, it's neither the same or opposite. Right, so, right, essentially what we're going to do is substitute in opposite of x in the negative x in for x and see what our solution is going to get. Right, so if we substitute in x, negative x minus negative x, right, we end up getting negative x cubed, right, because it's an odd power, and this becomes plus x. So if we compare these two right here, we can see, right, we have the opposite of both terms, right? So the opposite, therefore, right, it's an odd function. Right? X cubed is now the opposite of itself, and negative x is the opposite of itself as well, right? So the whole equation became opposite, so it's odd. Try the next one. 3 times negative x squared minus 5. Well, when you square anything, it stays positive, so right, it ends up being the same exact function. So it's the same, therefore is even. All right. Next one, substitute in negative x, right? 2 negative x squared plus 7 times negative x minus 9. Square, it stays the same. This changed. So this is the only one that changed. So it is neither, right? This stayed the same. The 2x squared stayed the same, but the 7x changed. All terms have to either change or all terms have to stay the same to be even or odd. So it is neither. The next one, right? You're just going to get 5. You can't substitute it in, right? So they are the same. So it is even. Next one, substitute in negative x. 5 minus Okay, well, this term changed, right? But this one stayed the same, right? Same. This one's opposite, right? As this one was opposite and this one was the same, right? So if they don't all change, right, it's neither. Right? One stayed the same, one went opposite. Okay. Last one. Now negative x, so to the 2/3 is technically the cube root of negative x squared, right? Well, if you square anything, it stays the same, so it's going to stay as x to the 2/3. Okay. So it stayed the same, therefore it's even. Okay. So, right, again, you're just substituting negative x for all the x's you see. And if all the terms stay the same, then it's even. If all the terms are opposite, then it's odd. If some change and some stay the same, then it's neither. All right, then the last point of emphasis in this section is actually transforming polynomials, right? This shouldn't be too hard for you. Essentially, it's pretty much the same as what we've been doing for transformations, right? What you need to do is figure out your A, right? Your A, remember, tells you it's either stretch or compression vertically. Your H is a horizontal shift. And your K is a vertical shift. So this is just kind of reiterating things from previous sections on transformations. All right, so 5 tells us we have a vertical stretch of 5, right? Factor 5. Our H is 7, so we go right 7. And then our K is 6, therefore we go up 6. So right 7, up 6, vertical stretch with a factor of 5. Okay. So that's just describing the transformation, and then the next example is just matching a transformation to its graph. All right, so again, your A is -8. So right, -8 tells us that it's a reflection across the x-axis, right, with a stretch of factor 8, right, a vertical stretch. Our H is -1, so we're going left 1, and our K is 0, right? So we need to move our vertex left 1. So right, this is wrong, this is wrong. A and B, right, they both move left 1. Well, which one reflected over the x-axis? A did, right? So remember, if A is negative, it's a reflection over the x-axis. Okay, so that's how we find A. Right, so A was negative, so it reflected down, and it was stretched vertically because your factor of A was 8, and it went left 1 because your H was -1.